Good morning, everyone.
Good morning, sir.
Yeah, well done. Welcome.
Yes, sir.
Today, we would like to conclude what we started a few weeks ago, screen film radiography. I'll be wrapping it up with a little discussion on the things that go on in the dark room, at least about the film process. I'm just going to briefly see the major steps that dark room technicians can take in bringing out a film. Last time we wanted to look at the characteristic curve, that is the hot and then try, drip field the curve, but we were caught, we couldn't do that because of the time constraint. So today we want to finalize that and of course look at payment processing. Then by Friday or so, by Friday, we will have a quiz discussion which will be sent latest tomorrow. So let's conclude with, or better still, let's look at the HD curve. HD to be hotter. These two scientists or these two individuals, they work extensively on the characteristic curve. But I like to share the screen to make it come out much more vividly. So, I hope you can see what I'm sharing.
Yes, sir.
Okay, this is the HD curve, which is also called the characteristic curve. Characteristic curve. So it is a curve of optical density against exposure. Of course, you can see on the horizontal axis, at times it can be the camera, can be the dose, can be the exposure, as the case may be. So because they are all indicative of the amount of exposure that the film has gone through. Then on the vertical axis is optical density. And last time we defined optical density as the negative logarithm of the transmittance. And the transmittance is simply transmittance is intensity. Sorry. So transmittance is I over I naught. Where this one is the transmittance with when the film is in place, and this one is when the film is not in place. Transmittance you read out from the densitometer, and this is when the film has been put in place there. So from there we were able to define our optical density, OD, optical density as the negative logarithm of this transmittance. So we're able to do that last week. So today we look at this curve. It's a very, very important one for us in radiology because it tells us a lot about what we should be doing rightly. If you're not doing any procedure or any examination rightly, then if you look at the curve will actually tell us. Because if you look at this curve, we have three major areas on the curve. We have the flow area, We have the linear region, then you have the shoulder region. The toe area is the area of very, very low exposure, while the shoulder area is the area of a very, very high exposure. These two areas should actually be avoided. We don't normally do exposure within this two area, within this toe region and within this high exposure region. We basically make our exposure to be between along this linear region because it will give us a very, very good, of course, a very, very good radiogram. So how did it come about this optical density OD curve? OD curve is just you take out a film, just take out a film, you probably, of course, you expose it. Of course, you're going to make use of so many things for that. You expose it at a very, very low radiation level or low exposure. You get the point. You measure the optical density with the tensitometer. You plot it, you put it there, and so on and so forth. You continue until you get to very, very high exposure. At that time, when that region, when we have reached that region, you see something becomes almost parallel to the to the horizontal axis. At that point, one could stop exposing further films, and of course, one would then just draw this optical density curve. So it is not something beyond us. We can actually do it if we have a densitometer. But in our department, we don't have any densitometer. So if you look at this region, look at the toe region. Of course, it didn't cross the zero gamma axis or zero exposure axis because it is impossible to have them. Because this is actually a logarithm in the actual MOD curve. The vertical, the horizontal axis is actually the logarithm of the exposure. So we have in the toe area. If you look at a film, a new film that has been bought, without it being exposed, if you look at it, if you use it on a densitometer, of course, you shine light on it, of course, an ambient light on it on the film, you still see that the optical density will never be zero. You can never have a film whose optical density is zero. So that defines it will always have a particular number, a particular optical density number, which ranges from something like a 0.11 to 0.15. 0.11 to 0.15. That would be the base, the optical density of a freshly acquired film. Until without exposing it, it still has some latent OD in it. Should I use the word latent? Inherent, okay, we can say inherent. Anyway, inherent OD with it. So without exposing the film, it has this value range. This value range is that for a newly bought a fresh film. Then, when the film has been stored for some time, you store the film for some time. Of course, you could have maybe been inadvertently exposed, maybe with radiation. Of course, because most times the dark room is always adjacent to the radiation room. I mean the X-ray room in most facilities. So it is very, very possible that we still have some amount, some little radiation, of course, reaching the film. And with that, and again, heat the place the films have been packed will also experience some kind of hotter temperature, of course. And with that, you can have a slightly elevated OD if you measure it with a densitometer. Mind us, we have not actually exposed in this film. So with our film that have been stored for some time due to heat and whatever radiation, the OD we will have in that case range from 0.13 to 0.18. So this is the permissible optical density range we should have for a film that has been stored for some time. This is inclusive of the base and all this. So if you look at it, this 0.13 minus or 0.13 minus 0. Blah blah blah. We have around 0.02. So the heat, whatever, and the radiation would have had an additional effect on this base. So at the end of the day, we have this to be the, and again, if you measure a film after it has been stored for a long time, and the OD is greater than 0.2, it is advised that such films be discarded because it is seriously going to affect reading. You are having a film of maybe 0.4 OD when it hasn't been exposed. So it is going to seriously undermine the contrast we are going to get from such films. So such films, when it's been observed or when it's been measured to be above 0.2, the best thing is to discard it so that it shouldn't affect the contrast we want to get from such exposure. So this region, this 0.013 to 0.18, they define the base and the foreground region. They define the base and foreground region. So we have that to be around 0.18. Then slightly above it, if we begin to increase the exposure, the graph now begins to take a linear shape. At the end of the day, we have to have a very, very linear region till around the shoulder and portion when the exposure has reached a particular, a very, very high end. So we have so many things we can draw from the optical density curve, the HD curve. First of all, we look at the curve and the contrast. The curve has got a lot to do with contrast. Has got a lot to do with the sensitivity of this film, speed of the film, which is the normal language that we use. And we say we need them in high speed and film for a particular procedure. For some procedure, we might need them some very, very normal speed and film. So we can get all these information from a HD curve. So let's look at the relationship between the slope and the gradient. That is the slope or the gradient from an HD curve. We have on a HD curve, the slope at any point in time gives us the contrast of the HD curve. That is, at any point in time, we measure the contrast of this thing. We're going to have the, you measure the gradient at any particular point in time, you're going to have the contrast of such a film. For example, you have exposed a film at a very, very low exposure level at this point. If you take it, if you take the film at this point, you measure the gradient at this point. Of course, we all did the mathematics for adventure, as a few of us have done further mathematics, but that's not very, very, it's not a big issue. The ordinary mathematics, we know what is gradient is. Gradient is the change in y values over change in x value, horizontal over vertical over horizontal. So the gradient at this point is going to give us 0. If you measure the gradient at this point, we're going to have 0 because a change in y is about, a change in x. A change in x is the gradient is the change in y over change in x. A change in y here is 0. So we're not going to have any contrast at this very, very low exposure rate. But if we begin to increase the exposure, maybe we take exposure at this point, we're going to have a particular gradient, and the gradient at this linear portion, or the gradient at the linear portion is expected to be the same thing because it is a linear graph at this same portion. But in any case, we have a general language for defining contrast. And it's such that we measure at a particular OD level of 1. sorry, of 0.5 plus the 4 plus base. We take that point. Then we get here, we measure 1 plus 0 plus 4 plus base. So it is at these two ends that we now get a straight line. We now connect the 2 points and then get the slope of that curve. So the slope is going to give us the slope or the gradient of this curve is going to give us the average gradient or average contrast of that film. Because the film, we are going to be having so many gradients at so many points. We have gradients, differential gradient at this point, we're going to have particular gradient at this point and so on and so forth, at this point, at this point, at this point. But the general gradient we talk of in radiography is the average gradient, which is defined for 2 points. This point here, 1 plus 4, and then this point here, 0. I think this is 2. This is 2 or so. So at that point, we now find the gradient. The gradient, this curve gives us from a particular film that defines the gradient, sorry, the speed, the contrast of that.
Good morning, sir.
Okay, good morning.
Please, can you help us change the marker? We can't see what you're writing on the board.
Okay, I even forgot. I wanted to get a new marker. So many things. Okay,
thank you.
You're welcome.
So, sorry, sir. I'm not sure. I don't think it's about the marker. I think probably maybe the projector or what you're using is not really sharp enough to capture those images written on what you are writing on the board.
Okay, I think
probably maybe you can make some adjustments.
It's a combination of all these factors. The lighting, the environment, everything. It's a combination of so many factors. But I think a sharper marker will actually help us. I think this is slightly okay. This is a bit okay.
Yes, sir.
Okay. Let me go back to, let me stop the share and then space the board. I could have so if we have something like this, we said we can measure the contrast, the contrast of an elliptic curve is actually the slope or the gradient of such a curve. Like I told you before, the slope of a curve is actually the change in y over change in x, actually the change in horizontal over change in vertical over change in the horizontal. I said if you look at this basic curve, if you get the contrast at this point, actually the slope at this point, you're going to have 0 because there is a very, very little change in y as x changes. So delta y over delta x here, that is delta OD over delta exposure is going to give us a 0. As we continue moving at each point, we are going to be having various different gradients until we get to this linear region. At this linear region, the gradient at each of the points will always be the same. Because the gradient of a straight line curve is the same. There is no change at any point. Likewise, if you get here also, our contrast will now also turn to 0. Our contrast, sorry, our gradients will eventually turn to 0 again. So, but for general radiography, want to define a particular contrast, sorry, a particular gradient we use, and that gradient is the other contrast, for which is related to gradient, is called the average contrast, which is defined at 2 points. You take the point, this point of 1 plus 4 plus base. That is optical density of 1 plus 4 plus base. And of course, we know the highest for 4 plus base shouldn't be 0, shouldn't be more than 0.18. So we can simply have our upper value, which is a 1.18. So you just get your 1.18 here and then put it. Then you go up here. The higher limit is 2 plus 4 plus base. So you can have around the 2.18 here also, 2.18. Then you now connect the 2 points. You now connect the 2 points. At the end of the day, you find the gradient of the 2 points. So the gradient of these 2 points gives us the average gradient for that particular field. So for this particular field that has generated this OD curve, I mean the HD curve, the average gradient now defines the contrast of such a film. So and the acceptable contrast for any film should be from 2.5 to 3.5. 2.5 to 3.5. If you measure the contrast of any film and or you measure the characteristic, you measure the gradient of any film and you get it to be beyond the 3.5 or less than a 2.5, then such a film is not good for the purpose of whatever. It's not good for anything. So the film is best to be discarded. So this is one of the points we can draw from an HD curve, as if we can use it to find the contrast of a film. The contrast of a film, we said, is simply the slope of the curve. So if the slope of the curve, if you have two HD curve that have different slopes, it means they have different contrasts. That is, let me have you have two curves on this same axis. You have one, so you have one. I'm sorry about the marker. I now have another. We have this to be our A and this one to be our B. We have A here. You have a B here. These two HD curves have very different slopes because of the way they are. Because of the way and because of their nature. This one is a little bit, this one is steeper than this. This curve is steeper than this. So at the end of the day, this curve we are going to generate, this curve is going to generate a bigger gradient than this. And something begins to form, begins to flatten out, the gradient begins to go towards 0, 0, 0 until it becomes a horizontal. And becomes horizontal, the gradient has turned to 0. So the further this way, the steeper the curve, the better the contrast. So steeper curve, so curve A has a better contrast than curve B. If this is a film A, this is film B. Film A will give us a better contrast when we use it for exclusion. Use it to get the radiograph for palpation. We're going to have a better exclusion. So these are so many of the things that should actually be done when a new film pack has been bought. Check all these things to see if all these requirements, if the film pack passes all these requirements of quality control. So this is one of them. And another thing, let's see. So another thing we have to look at is the sensitivity of the film. how sensitive is a film? Contrast is not the only thing we look at in a film. We also want to look at how sensitive that film is. That is, how sensitive that film um, um, is used in a darkening forever. I mean, how much darkening that film can cause when exposed to radiation. That is how much darkening it can. So that brings us to sensitivity of the film, sensitivity. Sensitivity, which is also known as speed. This is a much more common term we use in defining a sensitivity. A sensitivity of a film is a term used to describe um, the level of exposure that a film will. Okay, let me put it this way. You are looking at having a film of 2 optical density, 2OD, and you have two films at that. The one that will give you 2OD with lesser exposure is more sensitive, 2OD. We're looking at 2OD for 2 film. Maybe the first film gave us an exposure, maybe it gave us a 2 millirange. Why to have an optical density of 2OD? Another film gave us 1 millirange. So the one that gave us a lesser exposure for the same optical density is the one that has more sensitivity, or put clearly, the one that is more sensitive. So this film that has, I gave us 1 millirange to cause a 2 optical density range, or 2 optical density value is much more sensitive than this. So for this, you can say this one has a higher speed than this. As if the film, this film A, let's say this is A, and this is B. So film B has a higher sensitivity than the B. Film B has a higher sensitivity than film A. So the term used in describing how much exposure is used in obtaining a particular optical density. If you have a lesser exposure, it means the one with lesser exposure is the one that has a better speed. Has a better speed than the one that used a higher a higher exposure to give a particular optical density. So in the earlier days, when calcium tungstate was the base, when calcium tungstate was the base for most film, we normally have 100 and speed film, 100 and speed, 100 and speed film. But today we have can have higher speed film, 200, 300, 400, and even 600 film speed. So the higher the speed of the film, the lesser the amount of exposure that will be used, the better for the patient. Okay. About 9 minutes. So let's see. Let me share another screen. So I have this slide to quickly explain in more diagrammatic fashion what we mean by speed of film and how it relates to the exposure level. If you look at these films they clearly have the same gradients, that is the same contrast. Why is that so? Because if you look at them, yeah, the gradient is about the same thing. If you look at this portion, they have the same steepness. Their curves have the same steepness, or basically the same steepness. So if you measure the gradient of these two curves, you are going to have essentially about the same thing. But the difference is in the position where they are. This one is towards the left of B. A of A is towards the left of B. But that is not that is not actually what we want to draw out here. We want to draw out which has more speed. If you look at this, we want to define, this is the definition for, this is the basic definition. If you want to define the optical density, or we want to define the speed of film, we base it on at the level of one optical density of 1 plus the value of base plus the value of the fog. So that will give us a particular value here, maybe 1.2 or so. So at the end of the day, to have this optical OD of a 1.2, this film A used an exposure of around 0.8 to obtain this optical density of a 1.2, whereas this other one used an exposure of maybe around 2.5 or so. So this one used an exposure of around 2.5, whereas this one used an exposure of around 0.8. So clearly, we can clearly see that graph A, the film that produced graph A is more sensitive because it used a lower exposure level to obtain a particular OD, whereas this one used a higher exposure. So for these two films, this one is much more sensitive to, it's much more sensitive than this. It has a higher speed than this. And by sensitivity, of course, that has a speed. We mean it was able to use a lesser amount of light photons, to affect the film And of course, by amount of light photons, we are directly implying a lesser amount of exposure, that is a lesser amount of X-ray, blah, blah, blah. So film A has a better speed, or rather has more speed than film B. I just want, let me entertain any question. Do you have any question before we continue? Okay, maybe no for now. So another important thing we need to note with film, why this change in speed of film. In some applications, we might want to have a film that responds very, very fast. For example, if you are dealing with angiography, of course, heart region, you want a film that has a very, very high speed, so that within a very, very short time, the film will capture whatever it wants to capture. For example, if you use a 600 speed film with 600 speed film, if you want to compare it with the 100 speed film, this one will take 6 times the time it will take this one to process the information as the photons are landing on the film. It is getting the information needed to form a very, very good optical density, blah, blah, blah. So this one is going to take, this film, 100 speed film, going to take 6 times the time it will take this 600 speed film to get a very, very good image. So it is when it is demanded, when it is required that something be sharp so that you don't have motion blurring, blah, blah, blah. It is best to go for high speed film, especially in angiography. Make use of high speed film. But in general radiography, don't require so much, except for maybe some heart, you want to take in chest radiograph. This radiograph of the chest, where we have some involuntary motion of the heart and then every other thing. You can hold your breath, but the heart continues to beat. So in that case, it is we might want to take a film that is slightly higher than the normal film we use for maybe other extremities, maybe bowel, I mean the pelvic region and so on and so forth. I will still have around 2.5 minutes. So I want to look at the relationship between the HD curve and the contrast again. But the HD curve contrast is not everything we want to look at. Of course, we want to have a film that has a very, very good contrast, but that is not all that is to contrast in a film. There's also something that is very, very key when you want to look at the film in terms of contrast. Form we have seen how the speed of film is affected by change in by maybe by a shift in the curve from maybe left to right. Okay, we have less than 1 minute more. Let me stop. Let me stop this and we'll connect again. I have to stop for now so that this doesn't cut any of our recording. Okay, you can join back again.